welcome to RF transceiver design course. We are discussing about the mixer design, and this is a passive mixer. Uh, we have seen a current mode mixer. Now we will see the voltage mode passive mixer. So the difference between a voltage mode passive mixer and a current mode mixer is this RF amplifier here. In the current mode we will have a transconductance. So, it is mentioned as a LNTA, low noise transconductance amplifier, and then we will have a passive switch configuration, and after that we will have TIA, trans impedance amplifier. So, here the in this case you have a current as an input and a voltage, because this current again converted to voltage by a trans impedance amplifier. Now, in voltage mode mixer, the input is, instead of LNTA, it is RF amplifier, and that is switched by the switches, and there is a buffer which has a input impedance very high. There is a big difference here between the TIA and the buffer. So, this buffer has a very high input impedance. So, this is a similar similar to the RF amplifier, and voltage mode passive mixer commutate the RF AC voltage, and in the current mode it is a current, and the RF amplifier driving the mixer is not fundamentally different from the current mode mixer. So, what is the distinction, what is the difference in terms of the passive mixer and this, that the key difference is a circuit that follows the switches. The voltage mode mixer drives the voltage buffer with infinite input impedance, that as I discussed, and current mode mixer have a TIA with ideally 0 input impedance. The RF amplifier preceding the switches operates similarly in both the modes. So, LNTA and RF amplifier means that is almost similar, because it is going to that switch is going to get the current. So, operation, noise and linearity. So, mixer operation, noise characteristics and linearity trade-offs are similar between voltage mode and current mode passive mixer, and current mode passive mixer are superior in terms of switch noise and distortion. So, current mode is the preferred choice compared to the voltage mode mixer. So, for LO driving requirement, active mixer can effectively use CML logic. So, in both the configuration that we have seen current mode mixer and this voltage mode mixer, the LO requirement is 25% duty cycle. Now, this if we compare this passive mixer with the active mixer, so active mixer can efficiently use the CML logic to generate the sinusoidal LO signal up to 1/3 of technology transit frequency. We already have seen the FT and how FT for the different devices or technology can be calculated. So, this if you want to have a active mixer, and then you can easily generate the 50% duty cycle LO, and you can operate active mixer at very high frequency also. Now, this passive mixer that we have discussed, the main requirement is a non overlapping clock with less than 50% duty cycle. Ideally, it is a 25% duty cycle. This limiting their use of a sinusoidal LOs. And in the, if we consider the 40 nanometer CMOS process, the rise and fall time are on the order of 10 picosecond. Therefore, if we want to design a 50% or 25% duty cycle LO design is limited to 12.5 gigahertz and 6.25 gigahertz respectively. So, at this technology at 40 nanometer also it can maximum the generation of LO frequency can reach up to 12.5 gigahertz, and this limits this passive mixer to be used at very high frequencies. Now there is a design, means there are a literature are available where while by using a 50% duty cycle also very high frequency passive mixer can also be designed. But if we want the configuration, if we want parameters and better design, then the 25% duty cycle is must, and which is uh, possible. We need to go for the lower node technology, 22 nanometer and lower node technology if we want to achieve a high frequency, or otherwise we can use the 50% duty cycle. So, this is LO requirement and LO generation is important in the passive mixer design. There is a blocker tolerant receiver. These are the two case studies that is provided in the book, that reference that is provided at the end of the slides. You can go through it. We will discuss that how you can make a blocker tolerant receiver by using this architecture. So, in many receiver architecture, the presence of RF filter is a crucial to mitigate the large out of band blockers. For example, in GSM, the powerful blocker is around 0 dBm and can compress the receiver and desensitize it. So, that blocker is important to block, and for that we required a filter. Now, this recent research efforts aim to relax our or eliminate the need of RF filtering, and the various topologies have been developed to achieve this goal. So, importance is a RF filtering. So, RF filters are essential for traditional receiver to prevent a strong out of band signals from the interfering with the desired signal before a down conversion. So, we have already discussed that how we can utilize this mixer, passive mixer to have a filtering, that is a end pass filtering. So, the choice of intermediate frequency whether 0 or not is arbitrarily in this architecture. All of them rely on a quadrature down conversion. So, we need to use a quadrature down conversion. So, the current mode receiver can be used here. So, current mode receiver rely on a low noise conductance amplifier followed by a passive mixer operating in the current domain. So, at this stage we already have seen that this is be a filter. So, if this is a TIA, which is a low pass filter in relation to this capacitor, this low pass filter will be up converted and it looks like a band pass for both the band, means double side band. Here the low pass is at single side band, and at RF input side it is a double side band and it is up converted to the omega low frequency. It can easily block the blockers, and when we use the filter out after the TIA, it will filter out the signal. It will only provide the desired baseband signal. So, how this configuration of current mode mixer, this is how it works. We can also use this impedance transformation property to realize this blocker resilient receiver. So, passive mixers in current mode receivers exploit the impedance transformation property. There are two key features of this. Low trans impedance amplifier input impedance is driven by a mixer which is with a low resistance results in a minimal swing at the LNTA output. And this low pass roll off in the TIA creates a high Q band pass filter at the LNTA output. So, that will provide the very high Q band pass filter, and that is not possible with by using the normal inductor based or any other active based filters. Good linearity at the RF front end and progressive filtering of the blockers along the receiver chain. A large capacitor at the TIA input helps attenuate the blocker, given that the TIA input impedance tends to increase at higher frequencies. So, we need to ensure that this impedance which is TIA impedance is properly designed, so that the when it is up converted on the RF side after the LNTA, and it will be down converted after the mixer. So, that will try help us to reject the it will help us to reject the blockers. So, now there is one very interesting receiver architecture that will emerge, and it is nowadays widely in consideration and in use, that is a mixer first receiver architecture. So, this study that whatever we have done of up conversion of the baseband baseband impedance, that will also help us to realize the mixer first receiver architecture. So, what happened up to now, we have considered the low noise amplifier block or LNTA block before the mixer, but can we remove that LNTA, because the LNTA has one of the limitation of that it cannot be a wideband and the software defined. However, we can make a mixer as a software defined by changing the LO frequency. So, if we discuss that external filtering in a current mode receiver. So, here current mode receivers significantly improve the linearity, and despite the improvement, external filtering like directly or through duplexer may still be necessary to tolerate the blockers like a 0 dBm blocker. And what we are doing here, removing the low noise amplifiers. So, an alternative proposal to enhance the receiver linearity and eliminate RF filters is to eliminate the LNA. Such a receiver configuration improves the linearity, but because we have removed the low noise amplifier, it will going to increase the noise figure, and the receiver noise figure, if we remove the LNTA. So, this is mixer first receiver architecture, where this can be different mixers, quadrature mixer, and the noise figure is depend upon the switch resistance R switch. So, we can find it out the noise factor, which is 1 plus R switch by Rs into V base noise of the baseband amplifiers divided by 4 mkt into Rs. Now, here m is a number of phase. So, if we use m is equal to 4 or m is equal to 8, we can reduce the overall noise factor of the mixer. So, here RSW is the mixer switch resistance, RS is the source resistance, VB2 is the TIA input noise voltage referred to each single ended switch, and K captures the noise folding. So, this is these parameters will help. So, if we want to improve the noise performance, then we need to reduce the switch resistance, and we can also increase the number of phases m. So, but it can have a noise figure around 2 to 3 dB. So, even if we try to plot the for this noise factor, and if we try to plot the noise figure, then for m is equal to 8 and current of the 1 milliampere, it can for different switch resistance R switch, which is starting from 0 to 50 dB. Now we need to also ensure the input impedance of 50 ohm, because antenna, it is directly connected to antenna. If it is not connected to antenna, we can have, in between we can have a LNTA, but here we do not have a LNTA in between. That is why we need to ensure the impedance matching also by using this T switch configuration. So if we consider the around 50 ohm, and if m is equal to 8, it still reaches a 3 dB noise figure or higher once the input matching conditions are met. So in practice, the noise figure can be even worse due to the parasitics elements that is not considered here. So what is still there are application exists where we do not have the requirement of very low noise figure. So the mixer first receiver with somewhat worse noise figure may be acceptable for low power application like Bluetooth or low power WLAN. In more demanding applications such as a cellular, the higher noise figure is typically unacceptable. So where the higher noise figure for IoT application also, high noise figure is acceptable, at that time we can use a mixer first receiver architecture. Even it can also help. There are many publication which is trying to, or many researchers are trying to achieve the more better performance by using a different configuration and analysis to improve the noise as well as improve the blocking performance. So it can be used in software defined radio as well. We can also design a noise cancelling receiver by using this combination of LNTA as well as the mixer first receiver architecture. So this LNTA and mixer first, if in combination of these two will be used, then the while at the baseband side, if we cancel out the noise which is generated by the RS, that can be cancel out. So this is a noise cancelling receiver. So in noise cancelling receiver, mixer first receiver can be considered as using explicit 50 ohm resistance for matching, and these receivers are linear and wideband but have a poor noise figure. So in noise cancelling receiver implementation, the main path provides a current measurement and matching is adjusted using the mixer switch and TIA input resistance. The voltage gain is Rm by Rs, that is a Rm is a mixer resistance, and auxiliary path provides a voltage measurement using a current mode receiver with a low noise transconductance stage and a current mode mixer. So the total gain is given by Gm into Ra. So noise cancellation is achieved by adjusting the feedback resistance of each TIA. So this is here there is a resistance Rm and here there is a Ra resistor. So the for this the gain is Gm into Ra, and for this it is Rm by Rs. So the we can able to do the noise cancellation by adjusting the feedback resistor of TIA based on a condition where Gm Ra is equal to Rm by Rs. So if we try to the case study which is given in the book, reference book, where they try to realize this noise cancelling receiver. So, a complete noise cancelling receiver designed for a wideband application. Here it uses 8 phases mixers for harmonic rejection and noise cancellation. The low noise transconductance linearity is critical, therefore, a complementary structure is chosen. So, complementary structure will help us to improve the linearity. The receiver noise figure is 1 plus gamma by Gm into Rs with noise contribution of TIA in the auxiliary paths suppressed by the RFGM cell gain. So, the measured noise figure demonstrate a sub 2 dB noise figure with a noise cancellation enabled, and the receiver combined the current mode receiver concept, noise cancellation and mixer first receiver idea for improved noise figure and linearity. So, if we have the harmonic recombination and noise cancellation block here, which will here the you can see this input impedance, we can realize the low input impedance, and this is a 50 ohm. Now, this is a noise figure of only this mixer first architecture, but if we try to use this auxiliary combination, then and if we cancel out the noise, the at the output we can get the noise figure of this complete receiver is less than 2 dB, and it is measured up to 2.4 gigahertz. So, it is a very wide band and low noise configuration that is help to that is designed by using this auxiliary configuration. So, mixer first in combination with the current mode mixer will provide the very good performance. So, there are various kind of configuration you can also make and design a good mixer first receiver architecture. So, this mixer first receiver architecture is nowadays widely studied and used in the literature. You can you can use all the understanding of that we have discussed during this entire lecture of the series of the lecture in the mixer design will help you to design a mixer configuration or receiver configuration, because mixer is a part of the receiver. Any receiver you can realize by using this mixer design. So, if we if I want to summarize here, we have started discussing the mixer design. So, initially we have discussed the parameters of mixer, various parameters like conversion gain, linearity, feed through, that all has been discussed. Then we have tried to understand the active mixer. So, one of the widely used active mixer, that is a Gilbert cell mixer. We discuss about the Gilbert cell mixer and how Gilbert cell mixer evolved, Gilbert cell active mixer. We also discussed the single balance mixer. While discussing the parameter, we discussed the single sideband noise and double sideband noise. Then after the discussing of the active mixer, we also discuss the noise in the active mixer, because flicker noise is important while designing the active mixer, and how we can improve the active mixer configuration considering the flicker noise. That also we have discussed flicker noise in active mixer. We also discussed then important is passive mixer design. We also started a basic passive mixer design configuration. So, we also discussed about the non return to 0 and return to 0 configuration of mixer, means passive mixer seeing as a non return to 0, return to 0, and we also build the analysis on designing the current mode passive mixer, where we try to understand the current mode mixer with quadrature configuration, and how the LO, duty cycle of LO, impact the conversion gain, and we understand the design of transimpedance amplifier and importance of TIA in designing the complete receiver configuration, how the impedance transformation happens, and gradually we try to see that how this passive mixer helps us to design a. So the fourth is a passive mixer, and it's widely used in the mixer first receiver architecture, and even in the normal receiver architecture we can use this current mode passive mixer for designing the receiver. So this complete series of the lectures on the mixer design will help you to start designing the mixer. We also have taken a case study on design. If you are interested more to study on this mixer design, you can in between one more point I want to add, that is we also have discussed the image reject receiver by using a hybrid coupler. This design will also be useful when we are going for designing a configuration for sub terahertz or terahertz application, because generating a 90-degree phase shift is difficult by using the normal RC at very high frequency. So, you can use a hybrid coupler approach to design a 90-degree to design the quadrature mixer. So, we also have discussed about the quadrature mixer. So, all these mixers, for more detail you can study from the reference book which is given here. So, these are the reference book will help you to understand. We will discuss more about the oscillator. Now, the next component, that is oscillator, will study the oscillator, voltage control oscillator, and then power amplifier we will try to see, and some of the basics of the PLL will be considered in the later on classes. Thank you.